Thanks for watching my demo. In the demo, you'll notice that the robot doesn't do all that much. It looks like it just drives a little bit and stops, which is what it does. But if you consider what a PID loop is, and if you know what that is, it's what helps the robot not come to a complete stop. And you'll notice that it stops pretty smoothly, that if it didn't, the battery and my computer unfortunately would have flew right off the top of it. So I just wanted to go over the code showing you what gave it smooth controls, what is ensuring that the motors know when to stop. Because if you'll notice, I didn't give it a command of start and stop. I just gave it a command to drive 1 meter. And I didn't have the measuring tape out, but if you'll notice, it went exactly 1 meter. So I'm going to be going over the PID loop code that I have right here. So it's a .ini file just to convert all of these bits to what the Arduino microcontroller understands. But this is written in C++, and this is part of the code. So to understand PID, I'm just going to go over a little bit of what that means. So PID is something where it's going to listen to a sensor, and then it's going to react accordingly to what that sensor says. So examples of this is like a water heater. Obviously, you don't want your water heater to overexpand or boil over or something crazy like that. So a water heater has a PID loop as well, where it makes sure that the water is just at the right temperature. And then it tells the heater, like, okay, you can heat it up a little bit more, or hey, lay off a little bit, so we can let it cool off a little bit so we're not overheating the water. Same thing, same kind of principle here. The PID loop works with something called an encoder. And that encoder gives the sensor reading, and then the motor knows exactly when to stop and how smoothly to stop according to the other motors that it's working with. So obviously, in a perfect world, the robot would have done that anyway. I would have just said, hey, drive 1 meter, and it would have done that. But unfortunately, we don't live in a perfect world. And because of that, we are going to, most robots, if not all, need to use a PID loop in order to properly control it. So I'm just going to dive right into the code now. And actually, before I do that too, PID loop is the proportional, integral, and then derivative. So if you've taken calculus, this should be pretty similar to you. Integral means that it's the opposite of the derivative. And then the derivative is basically what is between 2 points, like the smoothest line you can take. And then proportional, most people should know, but proportional just means like equating to or of something. So what I did is, let's see, and actually I can erase this later because I don't use set point. I use something else, use target distance down here. So I'll change that later. But for now, I'm just going to show you some of the variables. So the double output 1, 2, 3, and 4. So this is going to be a pointer. If you worked with C++, you should know what a pointer is. They're pointing, or it's a variable, but it points to specific, hence the name. It points to a specific variable. So it's not like the variable itself. So and output 1, that's how you write the like actual value of that pointer value. Or I guess you'll write the pointer as the double value there. And then the position, that is going to be changed by that sensor that I was talking about. So we're going to have to actually go down here in the code to see that. The position is going to be the encoder. So if this activates, this method activates, it's going to count. It's going to add to the variable count 1, and then count 1 is going to divide by 192.66. This is the average of what I did. I did a few different Arduino code systems, and to get around the same, I got around 192.66. So I drove the robot, like just myself and using my hands. I drove the robot exactly a meter 6 times. And this was the average of those 6 times. But you're going to want to divide count by what I found the average was when I got to a meter. And that's going to give you position. So the position is going to be what is it in relation to a meter. And how that activates is something called a interrupt. So attach interrupt, digital pin to interrupt, and then obviously this is pretty self-explanatory. The digital pin you're going to interrupt is motor 1 encoder A. I define that later up here. We don't need to read off all these, but motor 1 encoder A is going to be pin 19, so it's just going to read off 19. It makes it easier for later, especially if I'm probably going to have to rewire this at some point, either if the robot falls or something like that. And the easy part is I can just replace that. Maybe I chose 18 instead this time. So I just changed that from an 18 to a 19, and the code's all fixed again. So this makes this kind of coding where is definitely something you'd want in Arduino. You want to make sure all of the pins are defined, or that you use them in a variable. So like you can also do motor for enable and then equal 4. You just have to make sure the semicolon is after that. So once you do that though, it's easy to just replace the pins instead of completely redoing your code. So right here, we interrupt that pin. So if it feels like it's changing, which it should if it's moving and the sensor's working correctly, then it goes down here and it adds to that. And then like we said before, then it divides by the average of what I got from the encoder values. So all that is going to be relative to a meter. So that's what the variable position does. And then these are all of the variables that we're setting. Set point is 1. So set point, we're wanting it to have 1 meter in distance. And then the KP, KI, and then KD are going to be calculated itself. So it's usually a predefined variable like this. And I've never seen a code that uses different numbers than 1.0, 0.1, and 0.05. Of course, you can calibrate these items, especially if you notice like a robot or the PID system that you're using, like it doesn't matter what, it seems to be a little bit out of sorts. No matter what you do, you're probably going to want to go back to these values. For me though, it worked great. So I used those preset values and they worked pretty well for me. And then we're going to want to set the mode to automatic. That makes it so the PID, so automatic obviously just means that we don't manually try to calculate the variables ourselves. It makes it easier so we don't have to do calculus within our code. Or within the code, obviously the microcontroller is still going to have to calculate this, but then the other thing that I did notice that I also want to point out before I go further is the microcontroller is a lot weaker than a computer is. So what I've noticed happening is, and like if you want, one thing that I'll usually use to debug is and if you worked with Arduino at all, you need to start serial.begin 9600. That just sets it to 9600 bits to show the user what you're doing. So like right here, you'll notice I commented out serial.println finished. So this gives me the user input that says finished. But with it calculating all of this, sometimes it's a little bit hard to print this out on time. So I did notice, where is it? I did notice that sometimes I would get different values right here. So I'd get different values for position 1. And that's just because it's calculating all of these variables. And although Arduino is capable of doing that, it's not meant to do multiple things at once. So it's going to calculate these variables while it's taking in the input of that sensor. But I did notice while troubleshooting, seeing what was going on, is I would try to have the serial output show me something. And sometimes it would just come out a little bit more inaccurate than a regular Arduino code would. But on with the code. So just to finish up here. So the PID.compute is what actually, so set mode automatic doesn't automatically compute it for you, but this is what that is the .compute. So I calculate all of the motor one PID.compute, and then that allows me to that enables the variables that we preset up here into the PID loop to compute that. And then the rest is on the speed. So, or the rest is going to be on the speed and then the direction. So the speed is I set to constrain from 200 to 250. For Arduinos and motors, you can have a value from negative 255 to 255, and that's the max. But what if we say we do this, and this is actually what my code looked like before. So if we use negative 255, what it would do is it would first say, well, you want to go forward, so we're not going to do negative 255, but it would start me at 0. The motors are currently pulling a pretty big load. If I try to start it at 1 or 2, it's not going to move at all. So that's why I have it start automatically at 200. And if you noticed in the video, it does take a little, it doesn't take a ton of time, but it takes a little bit to move it. And then the Arduino kind of realizes, oh shoot, I'm moving kind of slow. And then they eventually push their motor speed or output to around 225 before it stops. But let's talk further about that. So this is how you write to the enable pin. Regularly, it would just look pretty much similar, except without the ABS and the parentheses. ABS just stands for absolute. You're never going to have a speed of negative 255. That's where motor direction comes in. So in the motor direction, what we're going to do is we're going to write to 2 different pins, high and low, and that's the only values that they really accept. So you digitally write, and the direct pin for motor 1 is high, and then for motor 1, the PWM pin is going to be low to make it go forward. And you'll notice not all of them are the same. So motor 3 actually has different value. The direct pin is low and the PWM is high, which is why I didn't write all of the motors the same. But then this is where the negative speed comes in. So later in the code, when I update this project, I'm going to ask it to go backwards. So if it gets a command like backwards, it's going to want a speed of negative 200 to 255. And although it can't make the speed negative, what it can do is it can change the direction. So now it understands, okay, well, the motor speed isn't greater than 0, so I'm going to turn the motor around. And that will enable the robot to have a technically negative speed. So that is the basics of my code. If you'd like to see the prototypes of it, I'll probably try to put that in GitHub later. But the encoder test that I ran, and then just the motor driving is probably going to be available soon in there. Let me know if you have any questions, and I would be glad to help. Thank you. Bye.